This time I want to talk about a homology or cohomology of a simplicial complex, but computed via a discrete Morse theory, assuming that this has some given gradient field. So first of all, let me recall for you how one computes the homology just in the classical, in the standard situation, where this is a simplicial complex. So from here, this is a simplicial complex. And so one is going to have, one has to take a look at the faces of K, all the set of faces and all different dimensions, but then one packs together cells of a given of the same dimension and constructs these free groups. Say I'm going to be using coefficients on Z, and so this is going to be the free abelian group on the n simplices, faces of K. Now, one has to be a little bit careful about taking an orientation of the faces. And for the purposes of this talk, let me assume that this is an order vertex, an order complex, in the sense that it has an order on the vertices. So I have a linear order on the vertices. Then, well, one can construct two consecutive ones of these guys. And the point is that one needs to define a boundary morphism. And this boundary morphism is defined as follows. Suppose one has a simplex alpha in dimension n. So this goes from vertex 0 to vertex n. And I'm going to be using this notation, meaning that these guys are ordered with respect to this numbering. And I'm going to be using the orientation coming from this ordering of the vertices. So I already have for free the orientation. So now one can define the ith face of alpha to be the same thing, except that I remove the ith vertex. And I take the corresponding orientation. I just preserve this thing. So essentially, this allows us to define, given a alpha and another beta, this is going to be an n-dimensional simplex. This is going to be an n-1 dimensional simplex. I want to define the incidence number on between alpha and beta, namely, how is alpha attached to beta? And this is going to be essentially -1 to the I beta, -1 to the I, if beta is precisely the ith phase of alpha, as defined here. And it's going to be 0, of course, otherwise. So essentially, we just want to this local information on how a simplex is built out of its phases. So the motivation for this sign is coming from a few examples. So for instance, one has, let me just use the natural orientation, this thing. So here is a alpha two-dimensional simplex, and one has to look at the boundary, and the boundary is, of course, this, then this, and then this with respect to this orientation. But notice that the orientation of alpha that inherits in this edge is the same one as the orientation of the edge following 0 to 1. That's okay. And this is because, well, this phase is obtained by removing 2. And 2 is, of course, even, so you get that they match the same orientation. So you only have in the boundary of this alpha being 0, 1, accounting for this. Now, if I remove 1, then it's supposed to have a minus sign, because this is the next one. So I get, but the orientation is, the orientation inherited by the orientation this is opposite, because this guy comes in this direction, and this was supposed to be oriented in that way. So this is because you get this minus sign, and so on. And you have, of course, you have higher dimensional analogs of this situation, one can have a vertex 1, 2, 3, no, say 2, 3, and 4. This is 2. So the orientation that I'm picking here is essentially going like this, using this direction, going in the base like that, and then going like that. So it's something like that looks like this. No, not so using that. Let me use this one. 2, 3, and this is the right hand. So this goes like that. So this goes like that, and like that. This is the right hand side orientation. So I'm using this orientation, and the last one goes in that direction. So for instance, this would be, here I have to remove the first one, the first integer. So although this would be 0 because I started with 0 here. Let me just rename this 0, 1, 2, and 3. So let's see, what is the 0 phase should be positive, and I have to remove this guy. So the phase that I have here is the one on the right. And I can see that this has to be coming with a positive sign, namely -1 to the 0, just because if I use this orientation and the direction I put it normal, in a normal direction out to the exterior, I get this orientation for this 1, 2, 3. So it's compatible with that orientation, and that accounts for this thing. For instance, what happens if I remove now 1? If I remove 1, I get the face on the back, and that has this orientation, namely, on the back, it goes like this. So this is like in front of us, and this is moving this way. And this is the natural orientation of that phase, 0 to 3, that goes like that, but it's incompatible with the orientation of the interior of the tetrahedron coming from the orientation that I already got in the tetrahedron, because the rule would say, okay, you have to push that in that direction outside the tetrahedron, and so the orientation goes the other way around. So when I equals 1, you get a -1, and so on. This is general in higher dimensions. And of course, you get this nice formula that tells you how locally, how this simplicial complex is assembled out of the several pieces. And the thing is that if you compute homology, you sort of integrate all this local information into global meaningful information for the simplicial complex. So in other words, the formula at the end of this allows us, then we can define these incidence numbers. And of course, the formula is just that you can write it as the sum over all. This is supposed to be a n-dimensional phase. So it's a generator of this free abelian group. And well, it's going to be a sum of all possible phases of dimension 1 less, but only those that are really part of the boundary, the actual boundary of alpha times beta. So this touches essentially, in principle, all the phases here. It's supposed to be a linear combination, but it's really touching those that make up the boundary of alpha. Okay, so this is basically the how you define this. And then you take a kernel divided by the image and so on, and you can construct the homology in a given dimension of this thing. So I want to do a similar, the analog of this using our gradient field. So suppose now that I have K with a gradient field on K. Now, if you recall the picture that I showed you at the very first lecture, where we had the torus standing up, and then we counted the critical points, we looked at the indices, and I told you very briefly that the boundary, one can make this sort of construction, but instead of using bases, one uses critical points. with some given index. And for instance, this in that case, this would be generated by, it would be the free group, the free abelian group generated by the critical points of index n-1 and so forth. And the boundary was given by counting the gradient flows, the number of ways for flowing from one of a critical point of index n to the next one, to all possible ways they can go. And this has to be taken with respect to orientation. So something completely similar is going to happen in this situation. So let's see. Now, the idea is that I want to compute the homology of K, and this is, of course, the homology of the cellular, in this case, simplicial complex of K. And this is supposed to be, well, this is hard because it might be there might be a lot of phases, and it's going to be a huge computation. But remember that K has the same homotopy type as the Morse model for K. Namely, we follow all the information for stretching for collapsing and pushing some of the cells to collapse some other cells. There are some cells that are not collapsible, not redundant, but its only job is just to be stretched to occupy all other positions and simplify the number of cells in this description. At the end of this deformation, one will have a cellular complex, not necessarily regular, with only the cells which are critical. So that means that, well, if I compute, if I'm interested in the cellular chain complex of the Morse things, well, this is in a given dimension, say n, this is going to be given by the cells already stretched that are critical and that lie in dimension n. So let me call this m star of K. And the purpose of this talk is to give a more explicit description of this, because if you want to describe it, you have to keep in mind all the possible deformations and redo the whole picture. But you can make a combinatorial counting of the corresponding incidence numbers, but now they are going to be a la Morse. Okay. So here, Mn then is, again, this is C3 on the critical cells of dimension n. Likewise, I have here n-1, okay? And I want to define a boundary morphism. So the question is, I would like to have a similar description to this one using some kind of incidence numbers for that thing. And indeed, since this is free, you take any critical cell, now it's a critical cell of dimension n, and this has to be some sum. This has to be a sum over betas of this dimension of certain numbers, but at a Morse, in the way that alpha and beta, alpha is hitting beta, and the sum taken over all the beta. So I want to describe these numbers. This has to be some given numbers. And for that, in order to have a better idea of what is going on, let me just reproduce this situation. So suppose here is our cell A, and then I'm going to be constructing this situation. I have here part of this thing. I have a pentagon here. 4, 5, base, 5, like that. And then I have this triangle, and then what about I have this thing? And suppose this is B. This is my alpha, and this is my beta. They are critical, say. And I've given this gradient field, and it would be looking like maybe this is stretching this way, and 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 also maybe this is stretching this way, and that, like that. So here's something that could be happening in our gradient field. And all the things that I've not put an arrow, they are supposed to be critical, but I'm just guessing how is the boundary of this attached to the cell in order to use it in that formula. All right, so what's the idea? Well, if I'm just taking a look, so suppose I have to take some given orientations of my cells, fix some orientation of cells. And suppose it comes something like this. And then this comes something like that, and maybe this comes something like that, and maybe this comes something like that, and maybe this is oriented this way, and so on. It was an arbitrary orientation. Now, what I want to say is how many times after doing this deformation, this is actually attached to beta, how many times it is running through beta, in which direction, whether it preserves the orientation or not. Let's do it geometrically. All right, so once I make this pushing, this thing travels this way and this way. So it's like opening up this gate, then the gas that is inside here expands, and essentially this guy becomes this and this. And now open up this gate. And then now this guy really does this, I already did this, and then comes this way. So this guy is really attached this way. And open up these and these gates all at once, and you will see that essentially this guy is following this. So this is all open. So this is all doing this, then this, and coming back. Well, open this one also until it reaches this thing. So at the end, some sections of this thing are attached to some other cells, whether they are critical or not, I don't care. The one that I care about is beta. But here, then some portion is going through beta in the positive direction. Another portion goes back in the opposite direction. So I want to say, okay, so there are two parts of this phase that are attached, that are incident to this beta and in a different way, essentially. So how can I do that? Well, let's see. Well, I already did this. For instance, this would have to go this way. It doesn't preserve the orientation that this line preserves, inherits from this orientation, given this collapsing, would be this. And I want to say, no, that's not compatible. Then I would have to do the next one. This will be opening up this direction. And yes, although these are not compatible, but these two are compatible. And then doing this and doing this, or the other way around. So how can I just keep track of this situation? Well, let's say this is A1, A2. Let's follow this A3 and A4, and then this. Well, I noticed that this is really a gradient path. I'm doing this, and finally I'm attached here. And there is another path that attaches in some other way. So what I'm doing is taking A, I care about this phase. Let me call it A1. This is A1. Then I take its pair, A1, and then take the phase A2. This is going to be A2. And so on, A3, A2, A3, A3, A4, A4, until I get this. I'm already here, 1, 2, 3, 4, and then I get B. Now I'm going to be calling, well, this is of course a path in the modified Hasse diagram that we introduced, where I've already, the original arrows were pointing downwards, and the new arrows coming from the gradient field are being now reversed. And I have this gradient, this path in the modified Hasse diagram. Now, let's, how can I decide whether this orientation is compatible with this orientation? Well, notice what we're doing is essentially replacing this line by this line. We're pushing this way, until it smashes in this direction. And I would say, no, they are not compatible. But I want to do this in a systematical way. So one way of doing this is looking, okay, not only edges were oriented, but also faces. Everyone is oriented. All the faces in all dimensions are oriented. So I can, since these two edges share this common coface, I could look at the given orientation of this A1, say this is the orientation of A1, and say, okay, let me compare whether this orientation is compatible with this in the usual boundary formula that I wrote, and whether this orientation is compatible with this. In this situation, notice that the incidence number of A1 in this edge is positive, because it goes that way, so it's compatible, and also this one is positive. So, but this orientation is not compatible because we need to do this. So it's not compatible with that one. So what that means is that the change in signs, whether they are or not compatible, is given by the incidence number of A1 into this guy that is A1 times the incidence number of A1 into this guy that is A2 with a negative sign. And the negative sign comes from the fact that instead of doing this and continuing in this orientation, what this guy is suggesting, I am actually collapsing this and I change the original orientation to this new orientation, right? So I need to put this minus sign. This accounts, this is my pivot, and I'm comparing whether these two are compatible or not with respect to this pivot, and recalling that I'm making a switch of direction, a natural switch of direction, because instead of going this way, this one is going to go the other way. Notice that this number would reflect the fact that whether these two orientations are or not compatible. Whether this sign is positive, it would mean that these two are compatible. And if this sign is negative, it would mean that these two are not compatible, independently of the given orientation of A1, independently of the given orientation of the small A1 and A2. For instance, let's change A1, capital A1, the other way around. If I change it, then both incidence numbers will change, and these two guys will change, and nothing happens. Now, if I only change one of these, say, it would mean that this would change, and it will be a change of signs, but now they are compatible. Now, this is precisely, before they were not compatible, but now this guy is being deformed in this way, and now they are compatible. So it turns out that this expression tells me whether this orientation of this edge is compatible or not with this orientation of this edge. And then I only make the product of all these things. And I call this the multiplicity, because I'm comparing this guy. Well, first I'm comparing whether these are compatible, whether these are compatible. Whether these two are compatible, and then whether these two are compatible, and whether these two are compatible, and the compatibility with the B. So I'm going to be calling this the multiplicity of this path and the path on the top, namely this one. This is the multiplicity of that guy. All right, but then I only have to do, if I want to say, well, what is the incidence number of this critical cell A into this of dimension n, into this critical cell of dimension n minus 1, a la Morse, Okay, well, it has to be a sum over all gradient paths. Namely, here's one way in which one section of this is attaching it this way, but here's another way of attaching it. And if you make the counting, they will adjust it. When you come here, it comes in this direction, and then it comes that direction. So at the end, it goes through and then comes over. And so at the end, they both cancel. So this is going to be the sum over all paths, gradient paths, taking into account the multiplicity, and this goes from this is a path from A into B. Taking a phase, like suggested here, and then it's phase, until you get to that. This is the sum over all those paths that you can find from this particular phase of A to this particular phase of A. And now, this is what I'm going to call the incidence number of A and B, but they are now critical. Notice that they don't have to be really one phase of the other. They might be far apart, and then you can just compute this incidence number. And then you can just plug in this information into that and say, okay, what's the boundary of some given A? Well, it's really the corresponding sum of all the ways A is inciding, I don't know if that exists, in all several A's, all several possible cells A. B's. So this is the sum over all possible B's of dimension n minus 1, and this is of dimension n, of the incidence number, whether it touches or not, a la Morse, times B. So it's essentially the same thing. It's just a way of encoding with some explicit numbers, formulas, how some given phase is touching and how many times, and whether it preserves or not orientation of all possible other cells. And then one can just say, okay, well, you can just compute using, you just check that this indeed defines a morphism like that. And not only that, well, this is obviously defines a morphism like that because I'm defining it on a basis, but that the composition of delta with itself going down 2 dimensions is trivial. So one can compute the homology. All right. So now, this is very intuitive. If you want to go through the details of this and make sure that all the algebra works, it's a little bit more of work, but this is basic idea. And well, what I want to do is compute an explicit example. You see that this is indeed doable. So let me work with this, my favorite example again, of the projected plane like that. And then I have this, and then I have 1, 2, 3, 1, 2, 3, and then I have 4, 5, and 6. And let me use the gradient field that I've been talking about. This looks like this. This vertex is really goes like that, like that, like that, like that. Three, 2 is already being paired. 3 is already being paired. 1, 2 is already being paired, and 1 is already paired. And then I have 1, 3 goes this way. And then I have this guy. Then I have this guy. And then I have this guy. 1, 2, 3, 4. All right. So this is it. Well, take my word for it. This is a gradient field. It is acyclic. And let's see, this is optimal in the sense that I defined. It's perfect in the sense that you cannot expect to do anything else better. Now, let me, what are the critical cells in dimension 2? These two cells hasn't been paired, and all two cells, all the remaining cells have been paired. Now, this edge is also critical, and the rest of them either are redundant or collapsible. And then we have this vertex, and all other are redundant. All right, so if I do this in this situation, the corresponding Morse complex, chain complex, has a Z in dimension 0, a Z in dimension 1, and a Z in dimension 2, and I need to count gradient paths from those guys. I know that the homology of this must recover because it only changes, the space only changes up to homotopy, and that doesn't change the homology. So the homology of that has to be the homology of the projective space in this case. And okay, let's take a look. So the generator here is the oriented critical cell 134, 134. The generator here is 25. And what we have to do is count the number with multiplicity of gradient paths going from here in this way, take a phase or three possible phases and make pairings until you get to 25 in all possible ways and counting the multiplicity. Let me do this in this moment with any kind of coefficients, integer coefficient, but it can be any group. All right, so well, let's see. Let's take a look at what happens here. There are three situations, there are three phases. So we have, let's think of this phase, 1, 4. So this is the phase of this critical A, and take this phase, 1, 4. Well, if I took this 1, 4 phase here, and I make the pairing, because I need to go up, and I need to make this pairing, I can only exit through one of these edges, but both are collapsed. So that's the end. There cannot be anything else because they are collapsed. They are standing here, they're being collapsed, and you cannot continue because this is a gradient field. So this leads to nowhere. There are no gradient paths starting here and possibly ending here. Now let's see, what about this guy? Well, I could follow this, and then if I follow this, I would be going there. Let's see. Sorry, no, this guy, no. I need this guy, right? This phase, I'm taking this phase. So, okay, I could go this way, and then I have two choices. Let me go through the bad choice first. Let me go up, then come here, and all of a sudden cannot continue. So going up, that's discarded. So the option is really going this way. Then I have either I hit what I need to, or I could take this, but this is a bad choice. So this is the only path, gradient path, that leads from here to here that I have to account for. Let me also analyze the paths going from this phase of this critical stuff. Well, let's see. This I could go is really this one. If I go right, bad choice. It cannot continue. Then if I go left, either I get to the place that I want to, or I continue this way, but then I get to the dead point. So there is again one single path that is this, going from here, doing that. So there are only two paths, and we need to count them with multiplicity. So I know that the generator here is really hitting plus, minus 2, or 0 times 25. If both paths have the same multiplicity, it would be hitting 2 or minus 2, but they could also cancel. and it would be 0. Of course, we know that the right answer must be 2 because we are in the real projective space. So let's, well, let's see what is the, if I do the, let's see, the first one, I could go through 1, 3. 1, 3 is paired to 1, 3, 5. And here I take the phase 1, 5, and 1, 5 is paired to 1, 2, 5. And here I take the phase 2, 5. Now, what is the, oh, yeah, I missed, sorry, I missed a something in that formula. Sorry about that. The incidence number, oh, up there. Here, counting. Well, you have to take into account the multiplicity. I didn't define it correctly. I'm missing this information because I'm comparing this, namely whether these two edges were compatible or not. This is measured here, this is measured here. And then I'm comparing this. This is measured by this number and also the corresponding numbers. But there is an additional piece of information here. What is the incident number, the sign on this regular complex of A into little a1? And that is, you have to take into account, let me just erase that, the index of A into A times that. Because this path really starts here, not here. So the thing that I wrote takes into account this and then takes into account that. Then for this path that it consists of this much, but also that, you can define this incidence number, and then the same formula would apply. So I was missing that number. Namely, I need to know what is the incidence number of this phase in here. I'm removing the very last one, so this is positive according to the first formula in the case of the triangle. And then this guy is positive also because I'm removing this one. This is, if I remove the first one, it's positive, negative, positive. So I remove the 5, it's positive. Here I have to remove this one, which is negative. And coming from here, I remove 2, which is negative, if I haven't made any mistake. And this is positive, right? But recall that there is a hidden sign here and a hidden sign here that comes from this formula. Where is the multiplicity? Ah, this one, right? So this means that anytime you have this mountain, this little mountain, it's because you have a pairing. And pairings, recall that pairings are switch the orientation. Instead of continuing the natural one, they switch it. So every time you have a pairing, a deformation, this introduces this strange sign. And I have here this one introduced by this, and this one introduced by that. So how many signs? 1, 2, 3, 4. This accounts with a plus, that one. The other one, so I already analyzed the one that goes, I guess, going to 1, 3. This one that goes that way. Now let's take the other one. The other one is, this one does not lead anywhere. And this would have to be 3, 4. All right. Then once I leave this critical cell through 3, 4, I have to pair it to 2, 3, 4. And then exit through 2, 4, which in turn is paired to 2, 4, 5 with these orientations. And then finally, I get the phase 2, 5. And again, I make the analysis of signs. This is positive. I'm removing this guy. Then I'm removing this guy. It's again positive. Then I'm removing the middle one. This is negative. Then I'm removing the very last one, which is positive. And then I'm removing the middle one, which is negative. And I also have to include the change of directions coming from the deformation. And hopefully I have, again, 4 negative signs, which accounts for another plus for this gradient field, for this path, for this gradient path. So at the end, what we are seeing is that the right answer is the Morse incidence number of this guy into this guy, which, by the way, are the only things that are relevant, is that it hits 2 times. It's not like in here. Notice that this is like a surface, orientable surface. We know that the other guy is non-orientable. This is why it's not something like that. Somewhere we are looking at this twist, and that it doesn't happen that this guy is mapping to this guy following positive and then negative direction. So what we got is that the homology, the homology of the projective plane, let's see. Well, the same way one has to analyze this, but notice that this is forced to be 0 because you can do the same analysis, just remembering that points are not oriented. They are oriented if they all have a single orientation, essentially. Or either you do the analysis, or, well, you say, if I take kernel, which is everything, and divide by something, I have to take the 0 homology, but the 0 homology is just the ring and cannot be non-zero because otherwise it would not make sense. So this is forced to be multiplication by 0. This is forced to be multiplication by 2. And then we already got that the homology here is Z. Here is Z divided by 2. And here there is no kernel. So this is 0 otherwise. And this works for any ring of coefficients or any group of coefficients. And in particular, the mod 2 homology of P2 is C mod 2 everywhere for star at most 2 and 0 otherwise. So this is this is actually quite geometric. This is quite believable. Just taking into account, keeping into account this picture. But if you want to do the right mathematics and check that everything is well founded, well, you have to read through the papers. All right. So far, so good. We've computed what we have, just understanding a little bit of how things behave, the orientations after the formation. But now there's an additional point that I want to bring up. I could compute also the cohomology with my Morse complex. Maybe I just dualize it. Take homomorphisms from each of the Morse complex in dimension n to some place that I want, and take homology. It's contravariant, so boundaries are the other way around, and you take cohomology of that Cauchy complex, and you compute the cohomology. But the cohomology comes equipped with these additional properties that are cup products. And I want to do one additional example to show you how to compute, for instance, a cup product. And for that, we need something more. If you want to do just homology, say for computing persistent homology or something like that, this would be enough, quite geometrical. But if you want to do persistent cup products or something like that, well, you can do the following. You need to understand a little bit more. We already know, let's see. So I want to understand the cohomology now of my complex, which comes equipped with this gradient field. And we know that this is isomorphic to the cohomology of the Morse homotopy model of K. That's perfect. And essentially, well, this is just the cohomology of the guy that was written somewhere, the cellular complex for K, which is, you can use just the Morse complex of our guy and dualize it. into the ring and compute the homology, the cohomology of whatever happens, like that. All right, let me call what is inside here M star K. It's just the dual of what we defined on the other side. Is you have this Morse complex, algebraic complex, chain complex, and you dualize it in the usual way. All right, so I want to get a hold on this, and here's what happens. I'm going to be describing, so far, this thing comes from the fact that K is homotopy equivalent to MK through a big mystery, through this way of deforming things, stretching, and these guys are the same, so therefore these are the same. But I want to give an explicit isomorphism between the chain complex of K, all faces, and the Morse complex of K as defined over there. So I want to give a couple of maps. They cannot be isomorphic. It's way, in general, this is much smaller in degree in each dimension. They cannot be isomorphic, but they might be chain homotopy equivalent. Namely, that you can have a map, the composite of this is homotopy to the identity here as maps of chain complexes, or that the other composite is also chain homotopy equivalent to the identity. And one can describe these two things very explicitly as follows. And here again, one uses the gradient field. So let me call this P and its inverse, P inverse. Well, let's call this way. And for that, I'm going to go back to that picture, but let me see. So where can I send a critical, a basic element? This is homology a la Morse. So the the bases are the cells which are critical. This is an n, let me call it, well, in n dimension, but this is critical. And I would like to say, okay, where can I send it? Well, according to that, this critical cell, now let me just define the other way, the other one, sorry, A. Critical. Okay, so think of that cell. It is critical, and it's going to be expanded to occupy other cells. In that case, it occupies A1, A2, A3, A4, and also the two that go below. So once the cell is expanded, it is no longer a simplicial cell. It's a disk, but it has been attached to other faces, but it's the sum, essentially, of all these simplices that it is covering when it passes through, finally reaching its destination. So let me send this into the sum of all this go from sum of B of B. Now B is critical. I want to see how this, when you deform it, it hits some critical cell. One say the A2 there is critical, so you need to see it would be A1 plus A2. So this is the sum over all B's of the sum over all paths U, taking into account its multiplicity, as long as U goes from B to A. Notice that in this case, A and B are the same dimension. This has to be preserved dimension. The dimension of A is the same as the dimension of the possible summands. And essentially what you're doing is then saying, okay, this cell is going to be expanded to here, and then it is going to be expanded to here. And when you open up, it expands into and takes into account all this, the sum of all those cells. taking into account whether this orientation is compatible or not with this orientation. For instance, when these two are the same, it really preserves the orientation, but if they are different, expanding this gas will reverse orientation. But an argument similar to that tells you that you have to take into account these multiplicity numbers. This is the sum of all, sorry, this is from A to B. Sorry. A critical, you have to, no, this is not critical. This is on this side. These are the guys that are critical. This is not critical. This is why I can do these sort of things until A is expanding. And if there is a path, a gradient path that goes from A to B, then it absorbs B. And this path can actually continue to another B prime, and you have to put it with whatever multiplicity of the extended path has. But you can change the path and take all possible, everything that it covers. Now, geometrically, it's quite clear that this must be what is happening. Technically, you have to, phases not only flow in this way, namely, not only they flow taking a phase and a pair, phase and a pair. They could flow also noticing that this is a phase of something higher, which is paired to, and then taking this phase and taking, this is a phase of something, and then they taking this phase, and then it's paired, and so on. So they can not only flow this way from A to B, but it could flow this way from A to B, except that in this case, the phase that we are fixing as our targets are critical. And being critical, they cannot be collapsible. So these kind of deformations are forbidden. It's only what they call the upper paths. You start first going up, going down, up, down, until you get all these things. But the other paths, the ones that are lower paths, appear here. Now I have here, and this A is critical. And now the inverse is given also in all possible ways this guy can flow. But now it is critical. It cannot be the pair of something, cannot go up, but it has many phases. And then it can flow. It can be take one of its phases, and it has a partner, phase, partner, phase, partner. But now you're going to stop at the same level and see how many times, how much of the cells it covers. So essentially, this goes in the same way. This is the sum over all possible B's, but now B is non-critical, not necessarily critical. This is the one that is critical, over the sum of all paths, but are going to be lower paths from A into B, although they have to be this way. They cannot start going up because A is critical of the multiplicity of this lower path times B, which is the same as that. Technically, one has to tell, as I told you, you have to take all possible ways of flowing. But when you restrict the situation to criticals being either the source of the target, you cut up in half the type of paths, either they are upper or lower paths. So, and the theorem here well, again, this is a little bit technical, but is that they are not isomorphisms, of course. This is much larger than this one, but they are chain homotopy maps. Phi and what I call Phi inverse are chain maps. Sorry, chain maps. Look. And not only that, their composite is homotopy to the identity. And actually, guess what is the homotopy? No? The gradient. The gradient goes up, and the gradient gives you a homotopy, essentially, with suitable signs and preserving, because you have to algebraize the gradient field. Before it was only combinatorial. But that's essentially the proof, and one inverse of the other up to homotopy. All right, this is also a very, very useful thing. Well, not only tells you, here is explicitly one way you can travel from one place to the other, but it has the following advantage. Makes these things more computable, for instance, for cup products, which I want to mention. What's the idea? All right, we can dualize this situation, take homomorphisms of these situations into some target ring now, because I'm interested in cup products. So everything goes the other way around, and now you have some map that goes from the dual of the Morse chain complex to the dual of the usual cellular complex of the K. And here I have the corresponding maps, but the duals, you have to dualize this formula. How do you dualize this formula? Let's say, suppose I start with some A. Dual. This is not really A. This is a morphism that is 1 in 1 in A and 0 all other basis elements. All right? So it's something that goes really from here into the ring. And I want to say, what is the dual? Where is this sent to? Well, I had to pre-compose with this thing. So I need to see what are the B's that hit this and with what number so that it is inherited in this formula. So what this tells you that this goes to the sum of all those B's that flow into B, into A. Gamma, taking into account its multiplicity. Because in the homology, I wanted to go from A up there to B, but now I am dualizing those. You want all those B that hit A with the same formula. So this is essentially the dualization, and you would imagine what type of paths this can be. The guy that is critical here is A, so this path cannot end up like this, because it's critical, cannot be collapsible. So its path is the one that starts, that has to be this way, from B, going from B into A. And there is a similar description for this thing. So what is the advantage of doing this additional step? Okay, now not only I have an isomorphism of the cohomology of K seen in critical terms or seen in classical terms. I get down into an isomorphism at the level of chain complexes. And the advantage of this is, if you're familiar with cup products, is that, well, cup products are defined really at the level of chains. Really, you can multiply chains. And if it is simplicial, there is a very simple, very naive formula that Stingray took up long ago. And it tells you how to multiply chains, cochains, in this case, the dual of chains. The problem with that is, well, okay, if you multiply two cocycles, the product is going to be a cocycle. But if you change these cocycles up to a boundary, the product will also change, but up to a boundary. That's a standard verification that one does. So if you divide by the boundaries and you just compute the cohomology, you can just put your hands on explicit representatives of the cohomology classes and do the computation. So, well, let me just give you, in what is left, let's do the same example as before. And now let's compute the cohomology algebra of the projective plane. Was it there? Now, recall that the homology, maybe already, here it is. The homology is this one. If I use integral coefficients, there is not much of a room for interesting products. Because, well, the generator here has to be the one that cup product multiplies, cup multiplies with anything without moving it. It's just the units. And this is the generator. Now, what I could do is multiply this guy, this generator here in dimension 1. If I multiply it by 1, I have said that this is not interesting, but I could say G times G. This is the only thing that I could do. But it is forced to be 0 because it would lie in dimension 2, and there is nothing there to receive this product. So, well, let me just, good news, let me do it with CIMAT coefficients. So I don't care about orientations. I don't care about multiplicities. I only really care about counting paths, gradient paths. And okay, so let's do it. And there is a room for some obvious, non-trivial product. Namely, take the generator in cohomology 1. And I want to decide whether the square, which lies, sorry. Well, I'm using the homology, but you know, if I dualize homology with mod 2 coefficients, I will get just there is no torsion, and you get only the dual, so I get basically the same descriptions. And now this would not change, but then this lies in cohomology 2 of P2, but this is non-zero. And I want to decide whether this is 0 or not. And do you remember what's the answer? What's the square of the generator in cohomology of the dimension 1? Have you seen it? Well, if not, no, the cohomology of P2 is polynomial with mod 2 coefficients on the generator of dimension 1 divided by that. It's a polynomial. All right, so we need to know that this is non-zero with an explicit computation. If I didn't know that, if I didn't know escission, invariance of homotopy, a little bit of coverings or spectral sequences or any kind of hard machinery to compute the cohomology ring, I could just choose and do it that way. Or if I'm interested in some database that I would compute products. All right, so let's compute that. Let's use CIMAT 2 coefficients. Okay, so now, let me erase a little bit. I might be needing this, but anyway, I'm really very bad at looking at the blackboard from the blackboard, and I never find the things. So it's the same for me to erase it and then write it again. All right, so what's the generator in dimension 1? Is 25 dual. This is the basic element. This is the generator. We already knew that the boundary going from dimension 2 to dimension 1 is multiplication by 2, but mod 2, this is 0, and the dual of 0 is 0. So there is no boundary to take into account. The critical stuff is already the generators. They are basis of, they are already cycles, and you divide by nothing. All right, so this is the generator in dimension 1, and I want to square it, and I want to check whether this is 1, 3, 4 dual. I'm going to do a little bit of computation, and it's going to be a mess. So I'm going to be, it's going to be a mess if I insist on putting stars. I just abuse a little bit of notation. Everything that I'm going to be writing is dual, and everything is not that generator, but it is the functional that whose value in that generator is 1, and on all other generators is 0. And for these purposes, just the map, there's no more generators. There is only one single generator. All right, so what's the strategy? So let me rewrite this. So 25 lies in the cohomology 1 of P2. This is the generator. And there is an isomorphism into the cohomology 1, let's say a la Morse. Here. What's the advantage of look, here I'm going to put, at this level, I'm going to put the simplicial situation. The simplicial picture. And here, I want to put the Morse picture. And I want to use the best of the two things and combine them. The advantage of being simplicial is that I know how to multiply duals of simplices. By the way, let me recall it for you, or maybe if you've seen this in your standard courses, what is the product of something of this form? Dual. So here you have some triangle in your complex. Here you have another triangle, and then you have the functional that is whose value here is 1. All other places is 0. Likewise for this. Now, well, I used not to remember usually, although I've even after many years, what is the formula? But let me tell you about that because, well, I just prepare it and more or less, but I've been using it for some while. And the situation is the idea of a steroid is this is an I-dimensional cochain, and this is whatever. This is a I minus j minus 1. Is that right? No. Yeah. No, I don't know. This is 0, 1. How many guys are here? There are j minus I. So it's minus 1 dimension. Because it's a number, but this is the number of vertices. 3 vertices can generate something of dimension 2. All right, and then the product is supposed to be, oh, right, so I said it wrong. Sorry, this is how it, so there are I plus 1 guys, but this is dimension I. Here there are j minus 1 guys. No, what you said, there are j minus I guys, and this is j minus I minus 1 dimensional. And now I want to produce something that lies in dimension j minus 1. Hopefully this is the right answer. Yes, because how many guys there are? If these are the same one, count this. What I want to say is this is going to be B0 up to BI, and then you just continue. B should have started from I. Sorry about that. I plus 2 up to BJ if these two guys are the same. If two guys are the same, they really connect, and you have this much and this much minus 1. You don't want to repeat it because it would not be a simplex. So, and how many guys there are? There are j precisely if you do the counting, and this is the dimension of this guy, and it is 0. You do all of that, and it is 0 otherwise. So the only thing that I want that one has to remember is that multiplying duals of chain basis elements is the only way that you can have something non-zero is when these two guys really match and join make precisely through a join the complete, the higher simplex. And if they are not, then they cannot multiply it at all. So using this is the only thing that I was missing because I know how to compute. If I have a basis here, say you have an element here. Well, you would need to have an explicit representative, a cocycle. If you're lucky enough to get a cocycle, then you use, and you want to multiply this E with another E prime with a cocycle. Well, the rule says, say any representative, make the cup product with the other guy, and this is guaranteed to be a cycle, and then take the cohomology, and this is by definition the product of E times E prime, and by the way, it is anticommutative and all that stuff. But it depends on having explicit cocycles representing these cohomology classes. And it might not be quite accessible if this guy is too strange. But on this side, well, this has much less generators, and it might be easier to get, at least with the help of a computer, or in this case, just by looking at this picture, you have explicit generators. Here, the boundary cophase is trivial, so the actual generator is a cocycle, and that generates that thing. So here I'm lucky enough to talk about actually the cocycle. This is this thing, the dual of that thing. So now I can, well, I need to bring it down with the formulas that I need to do what? Well, this is a critical stop. So I need to go from all possible ways of going from these simplices up, down, up, down, up, down, until down 25. Finishing with a down. Cannot finish with an up because this is not collapsible. So I need to understand all possible ways from starting from something of dimension 1, going up, going down, going up, going down, until I go down to 25. All right, so let's take a look now to the geometric picture here. Let's see, whatever this path is, I need to count this number of paths and remember where they started. All right, it has to end with something that has 25 as a face. Well, 25 is the face of only two things. This guy and this guy. 25 is the face of that. So I have two possible choices. This can be the face of either 2, 4, 5 or 1, 2, 5. Both have 25 as its face. I'm not going to be worrying about multiplicities because signs are irrelevant. I'm working modulo 2. And now, well, this is forced. What is the friend of 245? 245 is, sorry about this, this was like that. Okay, so 245 is paired to 24. 24 is pushing and collapsing this guy. And 24, I need to take a co-face of it. That is not this one, because this is the one that I change orientation in the Hasse diagram. I need to take any other possible choices. But luckily in this case, 24, namely this, is only the face of that, but that's already been taken here, and of that, which is 2, 3, 4. 4. Then this 2, 3, 4 is the friend of 3, 4. And 3, 4, 1, 3, 4, 1, 3, 4. And then this is paired with no one. This is critical. Okay. So I need to take into account all possible ways of departing in dimension 2 from somewhere into here, or from somewhere into here, or that's it. And take the sum of all those with their signs, it doesn't matter. So this means that 25 here comes down in this diagram that I had into 2, 4 plus 3, 4 plus other possible paths, right? So I already had this and this. Now there is another possibility, namely this guy. So the friend of 124, 125, 125 is this one. So it's 15. And 15 is the face of 135. It's face of this and this, but it's already inverted, it has been reversed. So you have 135, and 35 is the friend of 13. And then this is also the face of 13, 13, 143, 134. Here is 13, which is here, and it is also the face of this triangle. And as before, this is the end. There is no further pairings here because this is critical. So I need to add this and this. Here is a path from somewhere into 25. here is a path from somewhere into 25. So you have to take into account 13 plus 15. And at the end, from the cohomology one of the thing into the cohomology one of the Morse or of the standard P2 in the simplicial terms, this is guaranteed to be a cocycle if you follow it. Just take the standard boundaries. This is guaranteed to be a cocycle, and it represents, under this isomorphism, the image of this generator, namely the generator in here. But I need to square it now. So I already used this because I have a good control on that, then a little bit of the flowing information, then I get this, then I need to square it, 24 plus 34 plus 1, 3 plus 1, 5, and do the product multiplication. Let's see what happens. Let's see, for instance, this guy cannot multiply with anyone because it could only multiply with anything starting with a 4. There is nothing there. Same thing for this. Same thing for this because there is nothing here starting with a 5. The only possible way is this can multiply with anything that starts with a 3. And then you have 13 times 34. So the answer is, this is 134. This is some cocycle. It's forced to be a cocycle because it's already in dimension 2 and there is nothing in dimension 3. It doesn't look very much like a cocycle, but it's because it's in top dimension. All right, and now, sorry, go ahead. And then I need to reverse the morphism. So I already had the answer. So I need this thing that is not guaranteed to be critical. I just need to see how it flows to the critical stuff. But this is critical actually. And there cannot be anything flowing from a critical into this critical, not even from below or not even from above, except itself through the constant map. Because I have 134 and I want to find some other critical. Actually, this is the only one, but that does this. Yeah, this is 34. And I need these kind of cells, which are critical. They cannot flow this way because they are critical. They are not redundant. And they cannot flow this way because this is already critical, not collapsible. So the only path is the constant path. And then this goes down up into 134, the generator of 134. But that's the generator of dimension 2. So this tells you that indeed the cup product, the square in the real projective space of the generator in dimension 1 is the generator in dimension 2. And this kind of philosophy, let me just finish. The point of this is that not only you can get it a hold on fundamental group as before, or in the cohomology ring, but you could also get a hold on anything that is defined in terms of cocycles or of cochains. There are massive products, for instance. There are higher, also the original proof of Jose Adem about the Adem relations and the definition, you can just work at the level of cochain complexes. And you can, in principle, evaluate Steenrod squares or on other kind of tools that come up in algebraic topology. So let me just finish there because I think my time is up. Please, if you have any questions.
So does someone has a question for Jesus? Yeah. Well, let's thanks Jesus again, and well, thank you. And